Okay. Hello, everyone. So we had it was a bumpy beginning of the lecture this time. So the setup is a little bit different, but for viewers at home, maybe you won't notice that things changed. But anyway, so the last lecture was quite eventful, right? There was a lot of discussions, and I feel that my plans were kind of foiled, and everything was okay. The lecture was derailed. This is my feeling. So I thought that we should do maybe take two of the previous one, take things we learned from last time, and try to implement it in a maybe more digestible way. Okay, so so last time we started to talk about first phenomenological observations that first pieces of input for our future deduction of the formalism, and we managed to to talk about two of them, but it wasn't very smooth. So let me restart and talk about them again, but this time from more mature perspective, let's say. So let me say it like this. Right. So the first. So we are dealing here, and our students, our slaves, they were measuring, quantum systems, right? But we don't know that they are quantum, right? Because we pretend we don't know anything about quantum mechanics. We just have this suspicion that maybe the system they were measuring there was maybe something odd about it. So like the first couple of observation tests, checks we should do is to see maybe it's not odd, maybe it's something we already know, right? So first couple of observations will be like probing if we are dealing with something we know, or is it something new, okay? And so we are role playing as someone who doesn't know anything about quantum mechanics, right? We are discovering it in this whole process, but we can claim that we are experts in everything else, right? We know everything about non-quantum theories. So we should. So our first observation should address this issue: are we dealing with something we are experts in? Okay, and there are a couple of general purpose things we can look to eliminate this possibility, right? Discriminate against things that we already know, and to really see that we are dealing with something completely different. And the first observation was it was a causality, which I won't write it again because we already did it. So remember, our inputs, the things we got from our students are those probability distributions, joint probability distributions, joint multi-time probability distributions. Okay, there is a sequence of measurements that was done, and from results, the student, the worker, the laborer estimated the probability distributions, and our job is to analyze those functions, right? And to, figure out what is the structure underneath. So our first observation is that when you marginalize, you take one of those probability distributions and you marginalize over the last input, you recover a probability distribution for a sequence that's one is shorter. It's just shorter, right? So what's written here? And I call it causality because now I understand better why it's called causality. Because last week I was apologizing that I don't have a nice story about it, why it's called causality. there was some discussions, and I think now I understand. So let me spin a story about this. Why we are testing this as a first thing. So this first test, looking for this relation that when you marginalize over the last one, you recover one shorter. It's a whenever, so we are probing if we're the systems we are dealing with, do we have to deal with time travel or not? Okay, so this is like really zero level check. Is there a causal structure on this system? Can we impose causal structure on this system, or we have to deal with tachyons, time travel, future affects past and stuff like that? And why this simple test of marginalizing over the latest tells us that we are dealing with causal system? Well, here is an explanation, at least maybe provisional explanation. This is what I learned from our discussions from a week ago. So OBS 1 causality. So we would say that okay. So we have our probability distribution and time probability distribution, right? We got it from measurements, and we say it has causal structure if we can rewrite it in a rewrite it in such a way that past events, future events are influenced only by past events, okay? And to formalize it, you can rewrite joint probability distribution like this in like a product of conditional probabilities, right? The conditions would be the past, and the probabilities for the future. And so we start with first measurement, okay, pick. Then we write, okay, T2 conditioned by what happened at T1. So there would be F2 conditioned on F1. Then the third one, conditioned by what happened previously. And so on until we get to the last one. Or you can write it as in a short form, 2n, 2n. P T J minus 1 . Do you see that it's like expresses the idea that only past influences the future, right? Right, because you have this probabilities that are made out of conditional probabilities that depend on the previous. There is no, the event at time T3 does not depend on the event at time T4, right, which is later. That's if you can write it like this, this means that you have a causal structure, okay? Future does not impact past. But you look at this form, and it also means that I can stick the last bit, this last bit, right? And when I inspect what is the remainder, right? It will just reproduce me probability that's shorter, one time point shorter, right? So if I take everything, collect everything in this product, except for the last guy, right? I will obtain here Tn minus 1 Fn, Fn minus 1. And the rest is would be a causal structure for a probability, gen probability where the, for the shorter sequence. Okay? Just algebra here. So if this is true, if this what we wrote here is true, then this guy here is a probability distribution, proper probability distribution, depending on the variable Fn, right? So it's normalized, right? So if I take this guy and sum it over Fn, okay, then I would just take away this, right? You just turn into identity. So I would get just Fn, Ptn, Fn minus 1 equals 1 times right, which is this is a causality. This is what we got. So observation 1, we are checking for this condition essentially, right? So if it was violated, it would mean that this causal structure is not applicable to our probabilities, right? But it's not, it's satisfied for all sequences. It means that this structure can work, right? So, there is no future doesn't impact what's past, and at least we don't have to deal with time travel. Does it make sense? Okay, so this is the story behind the causality. So again, this is a property that we expect basically from everything, right? So it's not like specific to quantum mechanics. It's not specific to any particular non-quantum theory or anything. This is what you expect if you don't involve tachyons, essentially. Which if you there are people who investigate what happens when there are tachyons in theories. There's Professor Dragan in university. He gave a very nice talk very recently on our seminar, and he was talking about tachyons. Don't dismiss it. Don't assume that there are no tachyons. You have to check. So this is the idea behind the causality. Okay, now let's go further. So maybe so now we want to see if we are dealing with something we already know. So we assume we don't know anything about quantum mechanics, but we assume that we know everything about all the other non-quantum theories. But is there a way to somehow, what is the common denominator between all those, classical mechanics, electrodynamics, hydrodynamics, some statistical physics? What is there some common characteristic of all those theories? Okay, so that we can check if what we are dealing with right now, it belongs to the same category as those other guys, right? It seems like a difficult question, and it's not simple, but if you think about it long enough, you can figure out that there is a common denominator, there is a common characteristic of all non-quantum theories, okay? And this common characteristic is, let's give it some name. Okay, so what's going on? Let's see. Złe narzędzie wybrane było. So non-quantum, we were using non-quantum because, okay, it's tempting to say that non-quantum are classical theories, right? But I realized I kind of painted myself into corner because on the first lecture I said like, oh, classical theories are those that they have interpretations that don't require measuring devices, essentially, right? And here I want to like maybe reclaim the term to use it for other perspective that we're talking about right now, but maybe let's go back to it later. So I'm saying non-quantum, you can think classical, but we have to explain it later. So non-quantum theories are, how to phrase it? Okay, maybe let's just. So a theory would be the standard non-quantum when it is possible. Okay, when the formalism of the theory can be reformulated. So, right, we started by talking about, you have your theories and they have formalism, they have interpretations, but the formalism doesn't really define your theory. You can reformulate them in whatever is more useful for you, like with Hamilton mechanics, Newtonian mechanics, and so on. So I'm like invoking this idea that you can have your theory that let's say electrodynamics, Maxwell's equation, stuff like that. I'm saying you can try to reformulate in a certain way, right? It's legal, it's allowed, and it's common practice even. So we are saying that if we can reformulate the formalism of our theory in such a way, that all its elements are derived from a master object. It's a weird wording. I will explain myself shortly. In the form of probability distribution on the space of functions. Parentheses trajectories. So this master object, this master probability distribution, it would be some functional, like with function of functions. It will be probability distribution or measure. And it operates on the space of of trajectories of functions. For example, functions of time. That's the simplest like thing to imagine. So x, variable x. Let me use some programming lingo here. So x is the variable that stores functions. Let me write it like this. So you know programming, right? You use Python. Are you aware concept of anonymous functions, lambda functions, right? So Python and basically all other languages allow you to store a function in a variable, right? So this is what I mean here, okay? So x is a function. It's a callable, right? You can call it with an argument, and then we just execute the instruction here, all right? So this is like I mean functions. They're like you program stuff, right? Function can be a variable for some distribution, right? Right? Because it's this is kind of difficult to properly write it down that you are doing, you have integration over functions. It's just difficult to wrap your head around this, right? So the notation is like, so when you see a square bracket, it usually means that you're dealing with functional. So the variables here are functions, right? Functions in this, in the sense that they store function that can be called with an argument later on, but it's a whole object, right? Like in lambda function in Python or anonymous function, right? Okay, am I going too far? Right, so this is like a probability distribution, but not on numbers like we usually deal with, but on whole functions, right? So it's a positive, it's normalized when you integrate over all functions, it's identity and stuff like that. And so this is like so when you have a theory that you can like rewrite in this form, and when I say that it's a master object, it's like, you basically, you construct your formalism in such a way that everything else in the formalism is just derived from this P, this master probability distribution, by taking some average with it or some, some restriction or whatever operation you need to do. But everything in your formalism is just derived from this one guy. Okay, it might be not very practical to do, but it's like the principle matters here. Okay, and you can believe me that every theory a non-quantum theory, can be like rewritten in this way. Okay, it's maybe not the most natural way of dealing with your electrodynamics or I don't know Newtonian mechanics of a material point or whatever, but it can always be done. Okay.
Just mean that these distributions will be pretty trivial. It will be 0, 0, 0, 0, and 1, 0, 1.
Well, it might be if
for given initial conditions.
For example, if you have you want to like project, reformulate your theory of material point into this form, then you have your Newtonian equation, like the dynamical law that allows you to generate the trajectories. Let's say this x here, this function s would represent the position of a material point. Okay. Then you can, given some initial conditions, could be a distribution, it could be even a probability distribution of initial conditions, whatever, and you could, but even it could be just one chosen initial position, initial condition, right? And you could solve your equations to generate a whole trajectory. for this initial condition. And now it would be very easy to define this master probability distribution. It would be just delta, right? So only our system is described by this one singular trajectory that is generated by our dynamical law in a form of Newton equation. If your dynamical law is Hamilton equations, for example, then those would generate trajectories which then you could, put under pack into this probability distribution, which doesn't have to. The randomness here. I mean, probability implies randomness, right? But randomness is optional here. You might have some randomness intrinsic to your system. For example, Brownian motion or something like that. The small particle in the fluid, it just bounces around, right? It's a noisy system. Then this probability distribution would actually, the X would be a trajectories of your Brownian particle, for example. And the probability distribution would actually be, would indicate randomness, right? But it could also have this distribution for deterministic systems, right? And then it would be just a filter. Impossible trajectories would have 0 probability. Possible would have some non-zero value. If only one is possible, then the distribution will be a delta, essentially. Okay, so it's like everything can be like molded to look like this. I mean, every non-quantum theory. Okay, and this is from mathematical point of view. This is just saying that all non-quantum theories can be described as a stochastic process, because this thing, this P here, this is something that defines a stochastic process. So it's like you have stochastic variables, Gaussian variable or something, have a number that have some distribution of values, can have whole spread of values, maybe randomly, maybe it means something else. So stochastic process is this generalization to whole functions, whole trajectories, rather than just single number. Okay. So from mathematical point of view, non-quantum theories can be viewed as stochastic processes, where randomness, usually we think about stochastic processes as noise. So randomness is like the point, but it's actually optional here. Okay, it can mean many things. It could be randomness, it could be something else. But the point stands that this is like, this is the common characteristic of all those theories we know. Everyone can be like reformulated to look like this. This is, I mean, it's kind of new idea, but not really, because if you are aware, and this of Bell, famous Bell inequalities, have you heard about those? The Nobel Prize was given a couple of years ago for experimental verification. So there was in the beginning of quantum mechanics, which we don't know the quantum mechanics exist, but we do know. But in the very beginning, when people started to like doing phenomenological, trying to deduce the formalism, and things were weird, right? So there was the famous debates between Einstein and Bohr. Right, and Einstein was like, wasn't satisfied, right? He was like, it all looks weird. That was his main objection. That is incomplete theory, because it's like lacks. Where are my trajectories? Essentially, he was asking. I mean, from the perspective of time, you can say that, but he was like that there is something. The description they were using, and we are still using essentially 100 years later, it's like it just doesn't feel right. Okay, so there was this idea that maybe quantum mechanics is incomplete. And then and it is very difficult problem to check this. Okay, how do you verify if something theory is complete or not? And then came the Bell. He came up with this great idea that this maybe rather than talking about incompleteness, he was like, okay, the whinging of Einstein, he like translated into his feeling that, well, maybe there are some hidden parameters real theory has some hidden parameters which our current formulation just is faulty and cannot access it. So he had to like came up with some characterizations of all those possible theories that would not have this problem, that all the parameters would be exposed. Okay, it's not like hypothetically quantum mechanics. And his characterization was this essentially. Okay, so he had, okay, so we suppose we have a theory with hidden parameters, which could be described formally as there's a probability distribution space of parameters. He was dealing with static case, so there was no need for stochastic processes. There just standard probability distribution was enough. And he was like, and he computed some predictions using this general form, which predictions which could then be compared with something that you obtain with standard quantum mechanical calculations. Okay, and the test. If you measured some stuff, calculate some quantity, some correlation function using all those results, and there was an inequality. If this value is greater than 2, this means that it could not be obtained from the theory with this kind of theory that's described by this probability distribution. And famously, quantum mechanics predicts that there is more than 2, that the inequality is violated, and many years later, it was experimentally proven that indeed this is how reality works. Quantum mechanics is not theory of this kind. Okay, so this parametrization of non-quantum theories in terms of stochastic process is not completely new, although I haven't seen like this clearly expressed like this, so boldly, but it's not surprising for people, because last week I was given seminar and when I said it to mathematicians, they was like, yeah, sure, no problem. We buy that this is like a characterization. So okay, so we coming back to our task at hand, right? We know from first observation, we know that we are not dealing with time travel. That's good. Now we want to see if we are dealing with this kind theory that we are experts in, right? Something that can be reformulated so that it's expressed as a stochastic process. And now, what is the test? What is the universal test that once you have this, what is the test that you can now employ? So there are like, okay, although it seems like, it's just, it's just something, whatever, but just assuming this form, there are a lot of consequences from that, okay? And then most of those consequences, it's like, okay, since all the theories, non-quantum theories that we know of, are of this form, that our like intuitive understanding of of measurement, of observation, and even of ontology or epistemology of physical theories is kind of informed by this, this trajectory picture. Okay, so it's like, and this trajectory picture it narrows down many of those things into very specific, with very specific constraints. We don't think about it too much because this is what we are used to. This is how world works for us, right? This is our intuitive understanding. But, now we can like think about it a little bit more deeply, because we are facing a possibility that we will have something that actually breaks out of the mold, right? And there will be some unintuitive behaviors, and we want some simple tests to see that. So since we are talking here about measurements all the time, so what are the consequences of this trajectory picture for measurements? So last week we talked about it at length. So I give you here a short summary. So since this P, this functional, this distribution is like your master object, everything has to be derived from this. So if you think about measurements in this kind of theory, so we want to have your joint probability, joint multi-time probability distribution, it has to be extracted from this guy. And this extraction is formally, you do it by taking a restriction. So this is a distribution of whole functions, but you are interested at like probing those trajectories at some time grid, essentially, right? So this extracting this joint probability distribution is a like very, very standard thing. So the joint probability like this is obtained from this master object, this master distribution, by taking I don't know how to call it. It's formally called restriction, right? So you take a product of deltas where you say, I constrain my trajectories so that the value at time of trajectory at time tj equals xj, okay? You have product for all time points. So you asking what is the fraction of all possible trajectories that satisfy the condition that at those chosen time points, they pass through chosen values, okay? And you integrate it with your distribution, okay? So that's measurement. So how you describe measurement. So if you assume that this master object exists, this is how you describe measurements. And now there is a very like big consequence of this formula, which we talked about last time as well. So this thing implies that if you take any of those probabilities describing measurements and you marginalize over arbitrary argument, you get probability distribution it's shorter by this chosen argument. This is called consistency. Consistency condition. Okay. Noted. So you can, I hope you can see how do you, if you have this, assume this, that P exists, this P, functional P exists, and multi-time probability is defined like this. Then when you marginalize, right? So you sum over like here, that means you come inside under the integral, you find the delta corresponding to argument xj, and you sum over all values of xj. This eliminates delta, right? Turns delta into identity, into one. So it's just disappears from this product. But one delta less is just another multi-time probability distribution, just one that doesn't have this argument at this time, right? That's why you have easily, you get this, right? So assuming trajectory picture, so if you have trajectory picture, valid trajectory picture implies consistency, but amazingly, this is very strong. There is a implication other way also. So you might say, okay, I assume my theory is one of those with trajectory picture valid, right? Then I have consistency, but you can say, okay, let's say I'm doing phenomenological approach to my phenomenological investigation. So I have access to probability distributions. How can I check if this master probability exists? And as it turns out, if you have a collection of probabilities like this, and they are consistent, this implies that this P exists. Okay.
I'm sure. I don't see this equivalent that it necessarily from this construction of this master object that the consistency should follow. You mean that?
I mean, you mean implication downwards?
Yes, like implication downwards.
Okay, so let me calculate it quickly for you. So I have my integral, I have my deltas, xtn, xn, and there is delta corresponding to time tj, right? You see it? And you come in with a sum over xj, right? And you have a probability, right? This is what is this? This is one, right? Just remove the constraint, and because those are constraints. Of course, we are assuming for simplicity that the discrete values, the x functions x have discrete values. If they were continuous, you would have Dirac deltas, and you would deal with distribution, not functions, but we don't want to do that. And when this guy is it's one, is just not present here anymore. So hence you get this, right? Okay. But this going
just pretty the first glance because on the level of deltas it's clear, but like that this object that it should boil down exactly to this trajectory without this point, this probability, this master probability distribution.
I know why you are like worried a bit.
Necessary condition, not sufficient.
It's sufficient and necessary.
Because what if you try to, I mean, this works any measurement variable, because you are using only x variable, but if consistent condition actually works for all type of measurements operate.
We'll get to that. We'll get to that in like 10 minutes, because you're asking what about, so if this trajectory x represents observable, what about many observables, right?
Yeah, for example, quantum mechanics.
I mean,
if you only consider
we'll give me 10 minutes. We'll talk about this in 10 minutes. This is very important thing. So it's implication. So if you are not sure if this master probability distribution exists, but you have access to all the although those multi-time, discrete time distributions, and they are consistent. There's a theorem, extension theorem it's called, Kolmogorov extension theorem even. Like everything in probability theories, Kolmogorov this, Kolmogorov that. So if you can reduce master distribution into discrete time, you can extend discrete time into master. Okay, so you can like, if you have all of them, you can like, you can recreate. In principle, there is a procedure like limits. There is a proper limit you can take where you could, if you have a collection of consistent probability distributions, you can just take a limit where the time points become, infinitely many time points in your grid, okay, which would give you then this master probability distribution. But it is also a test, right? Because we are dealing with phenomenological probability distributions. We check that they are causal, which, causality looks kind of like consistency because you marginalize over one of them and you over the argument and you get probability for shorter, but it's unrelated. It just looks similar, but it's completely unrelated to this consistency here, right? So therefore, if we want to see if we are dealing with, we know we are not dealing with time travel, that's good. Now let's see if we are dealing with something we already know. Are we dealing with a theory of a valid trajectory picture? Because if we do, we have all those probabilities. There is very simple, well-defined path how to like completely characterize your theory. Because the master object can be recreated from things we just measured. So it's just simple matter of, there is a procedure you can imagine that would give you everything, your equations of motions, if there are any complete characterization just from this point. So we are checking so we have to check for consistency essentially, right? If we take our probabilities from experiments, we find that they are consistent for every sequence, for every choice of times, everything must be always consistent, right? Then we know we are back on our standard field of expertise. There's nothing to see here, we can go home, right? And of course, we do the test and we go to observation 2, inconsistency. There are cases, and it's enough to show just a couple of cases where you marginalize and you don't get the shorter one. Okay. So if it was consistent, you would get 0 here. If you take the sum, it's inconsistent, there is some remainder here. Okay. It's at this point we don't need to know what the remainder is. We just witness that this is not theory with valid trajectory picture. And it's like, it's enough to show that for a couple of situations, you violate consistency. It already tells you that you cannot, this master probability distribution on a space of trajectories does not exist immediately. But in fact, if you are doing measurements on quantum systems, it's very, very difficult to find cases where you get consistency. Okay, even though mostly consistent, it's difficult. Okay, usually when you start seeing this, it means that your quantum system is kind of in classical limit, basically, right? So the first observation is that we are dealing with causal theory. Second observation is that we are not dealing with valid trajectory picture. This is something new, completely new. And knowing that, knowing that most of our intuitions about measurements come from working trajectory picture, now we have to we are on, uncharted territory now. But the fact that we know we cannot describe observables like trajectories should now inform us what to do next. Because if it's not trajectory theory, then what is it? This is our job. We want to deduce what is it. If it's not trajectory picture, then what is it? Okay. So now we have to figure out what are the next steps? What are the next measurements we want to analyze? And from what angle? What are we fishing for? And so now we'll the questions. Now the questions, okay? So we have to, again, since we are familiar on an intuitive level with theories that have that trajectory picture theories, we now have to challenge our intuitions about measurements, okay? And there are good conclusions you can draw from those intuitions, and there are bad ones, okay? First, I want to address one very common and very bad one. There is this idea, if you had some experience with quantum mechanics, you most likely heard about this something to the effect that measurements in quantum mechanics are invasive. And this is in contrast to classical non-quantum theories where measurements are essentially non-invasive. So there is this invasive versus non-invasive dichotomy. There's this idea that fundamental thing about quantum mechanics is that it has a invasive measurements. This is what makes it different from non-quantum theories. And this is, and I want to show you some arguments that this whole idea is just flawed. It's completely flawed. It's not. If we just stick to this idea, we wouldn't progress. Okay, there are better conclusions, but this one, it's kind of Hubert. On the previous lectures, he was alluding to this invasiveness all the time. This is how people think about, you do measurements, there's a quantum jump. When you observe, stuff changes. This dichotomous mode of description that I characterize standard quantum mechanics as, it basically implements this idea very explicitly, right? You can say that it's built around this idea that measurement in quantum mechanics should be fundamentally invasive. And I want to challenge this. Okay. After some thought, I realized that this is kind of bullshit. Okay. So invasiveness of measurement is not a primordial concept. It's a derived concept. It's derived from non-invasiveness. Okay. It's kind of weird because you would think that invasive was first and then non-invasive is just negation. But actually, non-invasive is primary, and then by negation, you want to get invasiveness. And
something being invasive. Measurement being invasive. It's just, I would say that it's deeper in the sense that we believe that measurement is just the process of picking a value for the system, and that its value is somehow inherent to the system. That I have a free particle, and this particle is traveling in the space, and I believe that in every moment of time it has some position.
Yeah,
And it's well defined, and the fact
the
that
tree-
you measure it is just that they think it's somehow.
does
But it
tree
was there.
does tree make a sound when there is no one to hear it?
Yes,
Right.
exactly.
So is there a trajectory where a measurement is just probing this trajectory, but its trajectory is just unravels in time independently of the intentions of observer? This is like
a little bit of the belief that we do not live in a simulation, or at least not in an optimized simulation.
or to put it or to really put it more concisely or more precise and concisely. It's like, can I, so let's say I have some description of a system, right? Can I do measurements in such a way that I'm like that the results of my measurements will be described with in the same language? So can I because in standard quantum mechanics you have one description for when there is no observer, right? You just some states, density matrices, unitary evolution. There is some mathematical formalism, and there is separate method for describing what measurements shows, right? And this reinforces the idea that measurement is invasive. Actually, it's built around this idea, because if it's invasive, then what I see is inherently has to be disturbed by me looking at it, and so what I'm seeing has to be something different than what would happen if I didn't look. So I have to have two modes of description, right? That's why Einstein was like, dude, this is just, it's wrong. I mean, my measurements don't reveal what the system is. It's tainted by act of measuring. So what measurements means nothing then, right? It's like, there should be this something else. And you could argue to Einstein, well, look, man, measurement you have to couple with the system. You know, there's some interaction. Of course, it has to disturb stuff, right? Maybe it's just impossible to see systems in their virgin, untainted glory, pristine glory. It's just measurement has to do something to your system. But then the counter is, but non-quantum theories, they don't have this problem because the measurement there is non-invasive, right? So it should be possible because, classical physics works like that. And now, okay, why do you think it works like that? Where this comes from? And it comes from a very specific thing, okay? So if you look at the consistency condition, we look at it once more. So we have a probability of doing measurements, right? Xj, x1, which supposedly describes a situation where we deployed our measuring device at all those sequence of times. We got our results, right? The probability of getting a particular sequence is given by this formula. We know that it comes from this master probability, right? On the other side, so I will be filling in symbols into this equation. We know consistency relation tells us that you can obtain from this probability the probability where there is Tj is struck out. So right, so when I sum over xj, right, I can produce a guy where this is cancelled, right? So this thing here tells us that the measurement was done. The measuring device was deployed at time tj, right? This guy here tells us, it describes a situation where the measurement at time tj never happened, right? This probability can describe situation when it's fit to describe situation when measurement at tj never happened, okay? So here we have a situation where it happened. Here we have a situation where it didn't happen, and the connection is through this sum, this marginalization. And typical way of, we are interpreting this consistency as, this is a necessary condition for having the trajectory picture, right? It's just a consequence of having valid trajectory picture. But typically people say, okay, so this means that the measurement was done, and the sum represents that the observer forgot what they measured, or they haven't noted it on paper. They just ignore it. They forgot. Okay, sum means.
It's a good way of checking
We
performed the graph or not. Because you can claim that you performed what you did, but you just forgot the results and you didn't publish it, but you did. So you can check it. What are the probability distributions? If they are such that there was an measurement, it means that indeed the graph was performed.
Yeah. So it's like so if we agree to interpret this sum, it's just some sum. It takes some function and sum. If we agree to interpret this as the measurement was done, but we forgot what we measured or something, or never noted it, didn't look. And this is equivalent of not doing a measurement at time tj because of the right-hand side of the equation. Oh, well, this means that the measurement, the action of the measuring device on the system has to be, if forgetting is enough to erase any effects, it has no effect on the system that was measured. Hence, essential non-invasiveness. Such measurements exist, so measurements cannot, in principle even, affect the measured system. Hence, classical non-quantum theories have non-invasive measurements. And now, okay, so now you go to quantum, you violate consistency conditions. So you have here, in quantum mechanics, it's not like that. Oh, so this has to mean then that measurements are what? The opposite. Why not? So they are essentially invasive, that you cannot avoid influencing the system. Hence, you need dual mode of description. Okay, so this is how the logic is constructed. All right. And now this is a faulty logic. Do you see that it's a wobbly, very wobbly logic? That it's what it really means is that non-quantum theories have valid trajectory picture. Okay. Quantum theory does not have valid trajectory picture. This is what it means for sure. Okay. Over-interpreting consistency condition as a non-invasiveness of measurement, it all hinges on this idea being coherent. That the sum represents something about a perception of the observer. It's a long shot, okay? The only, if it was like, this could work, you could make it work if those probability distributions here were really, the only thing they did was describe measurements, okay? If this was the only use case for those functions, only in this very specific case, then you could say, okay, if it's so specific, it describes just one thing, then maybe any mathematical operation on those functions also has to have some meaning, specific meaning behind this. Okay, this is like, so then what the sum could mean? Well, like, I average over, it's like forgetting sounds good. Okay. It's like, it doesn't make sense. And to make matters worse, this is a trajectory theories. They have this master object this is just one of the ways to restrict this master object to something else. And this multi-time probability distribution, it is fit to describe most of measurements, for sure. It's good for that, but it also describes many different things where there is no observer at all. Like interacting systems, you would describe with this kind of probabilities as well. It's multi-purpose function. So you don't even have this backup with, okay, it describes very specific thing about observers. It's not true even. So this sum over-interpreting is as a meaning that you forgot. You did, but you forgot. It's just, there is no, it does not follow, okay? It does not follow. And the whole construction, so whole idea of invasiveness and non-invasiveness hinges on this one thing here, okay? This is how I see it. And it's...
But with this forgetting, it's a little bit, because the measurement is some physical action or physical whatever that happens, and the outcome of a measurement is not necessarily connected with it. Like the fact that something is, some device is doing something to the system doesn't mean that it is being recorded what this device did, but it is still keeping doing.
Or in other words,
my automatic machine to measure my system, and I go out of the lab, it still keeps measuring, even though I do not look at this.
If you have measurements, I mean, if you think physically, what measuring device would have to do? It has to, come into contact with, have to interact with the system. And it's like a, basic principle, Newton's third law, whatever, when one thing interacts with other thing, the other thing interacts with the first thing, right? So if one changes the other changes the first, right? It's like, however, this is, so whatever kind of measurement you do, you can like idealize that the disturbance is small or whatever in some approximation, but this is not the issue. The issue is, so I have my measuring device on one hand. I have thing that I'm trying to measure on the other hand. They interact. And now I have like access to the measuring device, right? By inspecting this measuring device, what happens to it? Can I somehow read out what is this probability distribution, this multi-time probability distribution that characterizes the measured thing, okay? And it does not have to mean that they don't disturb each other. It just, what I'm requiring is that the description of how the measuring device changed would be like governed completely by this free, undisturbed probability distribution of my system. Okay, if this is satisfied, they could, I don't know, they could explode upon interaction. I just want to have a photo of of the moment of contact, right? And this is, so in other words, if I had my measuring device, and that would be some probability P, it's a system, right? So as a system, there would be a master probability distribution that describes it. So let's call it a O, because observer, right? And so if O interacts with, this is not very, it's like hand waving, okay? I just want to make some points. With X, we want to measure X by coupling with O and then, doing something with O afterwards. So we want to have this probability that governs the dynamics of O. So that if your description is in terms of probability distribution, so you have systems that interact dependent of each other, but you are focusing only on one of the subsystems. This is like doing open system kind of approach. So you have system A and system B, but you are focusing on only one of them. You want the effective description for only one subsystem. So this P of O would be, would be of subsystem O. So the general rule, if you think about it, is that this probability would be given by, there's certain kernel, depends on O and X. It is conditioned by X, and it's like averaged with free distribution of X, okay? This is like hand wave, but so if you have coupled systems, they interact each other, they disturb each other, there is a, some interaction. But now you switch to the, like you focus on one subsystem and you want to have a probability distribution. So you want to reduce the total probability distribution to only one variable, okay? So what happens in this kind of scenario, you get this kind of general form, okay? Because what else could there be? Some feedback loop? Because this means that there is some filter that filters the probability of X that you would use to describe it if there was only X present, right? What else could be here? It's the question. Some infinite feedback loop that is a X but modified by interaction with O, which then modifies what O feels, and then this modification goes back to X. It's like either infinite feedback loop, which doesn't make sense, or form like this, which is what actually happens. Okay, so now measuring device could disturb system X, but what really matters is that this kernel here, the interaction is, and the dynamics of this measuring device is such that this filter here, it's like allows you to basically get this part with little effort. Okay, it's not disturbance that's important. There's always disturbance. This is important. Is it possible to have such interaction between systems that this kernel here is a very simple filter that allows you as much access to this guy here as possible? This is probably too abstract. I apologize for that. This is how my my brain works. I apologize, but this is like, for me, it's. Are you aware of like I know what could help. There is this thing like linear response theory. It's often used in probing complex systems. So you have some complex system in equilibrium, and you poke it with external field, right? So you just knock it out a bit from equilibrium, and now you measure some observable on it. Okay, it's a setup for classical quantum system, whatever. And when this perturbation is weak, very small, you can write down what is the expectation value of your measurement, right? And you do the calculations, and you do classically or quantumly, whatever you wish, and you discover that this perturbation depends on some correlation function, but of the unperturbed system. Even though you are perturbing it, this is the point, you knock it with some external field, but the thing you observe depends only on equilibrium properties of unperturbed system. And it's when I read it many years ago for the first time, so I don't remember where, it was like, this is so mysterious that non-equilibrium, you have non-equilibrium dynamics because you poked stuff, but everything is given by equilibrium properties, as if no poking was employed. This is so mysterious because, we are disturbing the system, but it responds in a manner if it wasn't disturbed. And this is why. This is just general, because what else? Infinite feedback loop? That would make sense. Okay. So it's not invasiveness versus non-invasiveness. That's not the point, okay? And non-invasiveness is just, you know, it's just, oh, that's bad. Okay, you cannot, if we focus on this, we would go the route of infamous Greg Leggett inequalities or something that, so people try to capture this invasiveness in like more formal way, and it's a mess. Nobody understands it. It leads nowhere. So invasiveness is not the key here, okay? There is other thing, but we are running out of time. So I guess next time we have to talk about it, but it actually refers to what Tay asked, because there is one thing that's very intuitive and implied by trajectory picture, that if you don't have trajectory picture, it's like opens many options. So I would just, without showing where it comes from, so if you have trajectory picture, then there is only, okay, if you have a system, you have something that can be described in this trajectory picture, it automatically implies that there is only one observable, okay? There is only one observable. It could be like a vector observable that it has a couple of components, but there is like every observable you measure is the trajectory that represented has to be some function of certain elementary observable characterizing your system. Okay, there's only one observable. If you don't have trajectory picture, you don't have this constraint. Okay, because this having specifically one trajectory means that there have to be one observable. If you don't have this, all of a sudden it's possible to have many observables, infinite number even, as in quantum mechanics. And now this is kind of mind-blowing, because, you know, our intuition, the way we think about measurements, observables, and stuff like that is, again, informed completely by a trajectory picture. And now we are asked to extrapolate this, you know, the situation when there is only one observable to the situation when there is more. How can you do that from one point? If at least we had two observables, maybe you can imagine, okay, when there is third one, it's kind of like two, but more. But no, you have one singular observable. Everything is like, or your intuition is built around it. And now you have to say what happens when there are more. It's just, you know, just. But we'll have to do it. And we will do it, and it will reveal all the mystery around the quantum mechanics, okay?
The next example. But I think
oh yes, we will. We will basically, this will be our main tool for analysis, you know, to like for this observable. We will be playing with observables, okay? This is like this will be the key for everything, okay? But don't be, you know, be in awe. This is like completely, this is crazy. I mean, this is, you cannot imagine this, what it means that there are more than one observable. We are living in a world with everything can be explained as one observable, some fundamental characteristic that's always defined at each point in time.
So for Newtonian problem, like one particle, you have the trajectory of this particle, and from this
position,
you can deduce every property of it. Like
everything else is explained by first explaining position. Yes.
Okay, so this is the.
In electrodynamics, that would be a vector. So you have, you know, electric fields, magnetic field, which you can have as a one vector, and probably density of charges. It's like your one vector observable, and everything is explained through that. Okay, you see? that's why in classical physics, you don't talk about measurements, because all measurements are essentially measurements of this one elementary observable, and the rest is just some post-processing, whatever. It's not worth talking about. And it also kind of ties to the, so we have these competing definitions of classical. One was from point of view of interpretation that you can rely on. You don't have to introduce measuring devices, right, to have interpretation. That's I said that's classical. But here we have this. Okay, maybe classical should actually mean that you have this trajectory picture, and is there a relation between those two? Are they compatible, those two definitions? And I think there is case to be made that they are kind of related, because since trajectory guys have only one observable, so measuring devices are kind of trivial, because if you have some intuitive understanding what this elementary observable represents, you don't have to use measuring devices at all, because they are just, they work by fundamentally measuring the elementary observable, and there's just some post-processing, which could be whatever. So I think there is connection here. Okay, so those trajectory theories are classical, perhaps also in the sense of this intuitive understanding for compatibility with human understanding, or anthroposymphonic, if you want. It's a Greek for human compatible. So this is like, this is mind-blowing. When I discovered this like a couple months ago, I was like, oh God, this is so big, so fat. But anyway, we have to end. So we will continue next time, which won't be next week, okay? Because there's some conference, and they reserve this they reserve this room D, and I mean, I will think a bit about, maybe I will just do Zoom only, and then recording, or maybe I'll just skip. Maybe we need a break. No, we need project. I mean, we need internet and project. I mean, okay, at this stage, treat next week as cancelled. I will send email and stuff like that. If I change my mind that there will be Zoom only, I will shortly inform you. It will be, of course, recorded, so you don't have to attend. You can write later on, but it's initial assumption is that it will be cancelled next week. So we'll leave us hanging here, but I think we ended at the okay spot. We are moving very slowly. I'm starting to be worried a bit, but So okay, so ending the recording. So